Hi guys, welcome again. So today I have come up with a video that talks about the application of PN junction as a rectifier. Alright, and what kinds of rectifier we'll be dealing with? Half wave rectifier and a full wave rectifier. Alright, so let's begin with the topic. So in front of you right now you can see the setup of a half wave rectifier. Alright. So first let's just have a definition. Look at the definition. What exactly is the definition of a rectifier? Before discussing in detail the functioning of a half wave rectifier as well as a full wave rectifier, let's just know what a rectifier truly means. So rectifier is any device, any electrical device that converts AC, that is alternating current, to direct current. All right, so why this is required? So whenever we charge our cell phones today, we use alternating current, right? And that alternating current is transformed into DC because our cell phones are compatible with DC only. So similarly, there are certain equipments, lot of equipments that are working on direct current. So direct current is really the need of all the digital equipments we are using today. So this conversion AC to DC becomes really important. All right, so this device, this is just the beginning. The half wave rectifier that we'll be dealing with is just the start of knowing the functioning of a rectifier. So let's begin with the setup. Let's just understand the setup, what exactly we have. So we are using a transformer in this setup. As you can see, I have just boxed with a dotted line this primary as well as secondary. This composition, this whole constituency of primary and secondary winding is called as transformer. All right, we are using a transformer in this rectifier setup because we need voltage according to our needs, because we have connected a diode over here, so that we will have to look at the voltage, amount of voltage. It should be within our permissible limits. All right, so that's why we have used the secondary winding, so that we can adjust according to our needs what kind of voltage we need. Here we have supplied this alternating current voltage, and we will be getting voltage that is across A as well as B, already in the form of sinusoid. That is, this form will be there across A and B. Now the interesting part arrives. All right, the interesting part is we have been looking at the functioning of diode, how it functions in a forward bias as well as how it functions in a reverse bias configuration, right? So here is the real application of forward bias. How? Let's just see. So when we have supplied this AC, it is directly falling across A and B. All right, so this is the general sinusoid curve that we'll be having across A and B here. All right, now we know, all those people who don't know, that AC is alternating in nature, like it periodically reverses its direction. So in the first half cycle, this positive half cycle, okay, we have positive voltage at A. Is that understood? And during the negative half cycle here, because this is the property of AC, we can't do anything about it, right? AC has the property of reversing its direction after half period. So this is the full cycle. So this is the full cycle. This is one full cycle, and during one full cycle we have half positive cycle and half negative cycle. So the positive cycle, when it appears across A, our diode that is connected here across the load will be forward biased. So this is positive in the first half cycle, so this will be forward biased, and because it is forward biased, it will start conducting current, and what will happen? There will be drop of voltage across RL, and we will have a resultant voltage across RL that is only positive cycle will be able to pass and reach XY terminal. Here we have the characteristic. So in the positive cycle, this diode which we have connected here is allowing the current to pass, and here we have the resultant output across RL. Now what happens at the second half cycle? Second half cycle is negative. As you can see, it's negative, and whenever you connect a negative terminal of a voltage to a p-type semiconductor here, it becomes a reverse bias situation. And during a reverse bias situation, what happens? There is only one such current flowing through it, which is also negligible. That is reverse saturation current. I hope you remember that current. If you don't remember, you can just refer my previous video. Alright, so reverse saturation current is the only current that flows when a diode is in reverse bias situation. So what will happen? Since it is reverse biased, this is reverse biased, there is no flow of current and there is no resultant drop of voltage, because we know the Ohm's law, that is V equal to IR. If there is no current, there will be no voltage. Alright, because V is directly proportional to I. If there is no current, there is no voltage. Now I hope this is clear. So this happens continuously, and we keep on getting a graph. We keep on getting only the positive cycles, right? This positive cycle, this positive, and we keep on getting the positive outputs only. Now we are seeing this alternating positive outputs only. Now what about this thing? So this is a demerit basically, which is taken care of when we use two diodes. When we are using assembly of two diodes, we can get rid of the situation, and we can also have a positive output at this point. Now how are we going to have a positive output at this point? Because we will be using a full wave rectifier. Now let's just have a look at the setup of a full wave rectifier. Here it is. It is similar in terms of functioning of the half wave rectifier, just that we have added a diode here additionally. Okay, so this is the transformer. Now this transformer is a peculiar one. We are using this center tap transformer here, because from the center we have just taken out a wire and attached it to the ground voltage. Okay, so we are doing this so that in the negative cycle of an AC that we are supplying through this transformer, this terminal becomes positive. How? Let's have a look. So this is the voltage, right? This is the voltage that we have supplied, or that falls across this terminal A. All right, so this is the general sinusoid wave that we are getting. Now waveform at B. So when waveform at A is positive, because it's an AC, so waveform at B is going to be just the opposite of what it is in the point A. So this curve, all right, where it is positive it will be negative, where it is negative it will be positive, and so on alternatively. Now let's see the working. So when the point A is positive, look carefully, when this point is positive, this point is, when this is positive, this is negative. All right, now when point A becomes negative, B will be positive, and since B is positive, it becomes forward biased. In the second half cycle, here, let's have a look. Point A becomes negative and point B becomes positive. Since point B becomes positive, diode D2, which is at point 2, which is connected to the point B, will be forward biased, and hence it will be conducting current, and resultant voltage will be appearing across this load resistance. So since we were having this point missed out in the previous half wave rectifier functionality, so because of the presence of a diode D2 at point B, we are having this curve again. So we are having successive positive cycles here in this full wave rectifier. Is that clear? So now we can see it is not exactly a DC current, but it is flowing in just one direction. It's only in the positive direction. Earlier it was the wave was in the negative as well as positive phase, but right now it is only in the positive cycle. Now one interesting thing to do now is how to make this varying sinusoidal positive cycles into a constant supply of voltage. How do we do that? So because this voltage is not suitable for usage, right? Because it is varying as in the form of a sinusoid. It is not basically of any use. So to make it useful, we make use of a capacitor, so that capacitor filters out this sinusoid and gives us a constant value. Now how does it give it a constant voltage? Let's also have a look at that. Now we are done with the rectifier, right? We are done with the rectifier section, so we'll just be using a box instead of the full circuitry. So this is rectifier. So we have applied this AC across the terminals of a rectifier. Is that clear? So this is XY terminal that we have denoted in the previous design, that is here. Just have a look at that. This is X and Y. Alright, this is the same X and Y we are using here. Now this is RL, that is load resistance. It could be anything, any device across which you are looking, we are providing the voltage. Now see, this capacitor is connected in parallel to the resistance RL. Is that clear? So this capacitor will function as a storage, charge storage. Okay, this will store the charge. So in the positive cycle, what will happen in the positive cycle of AC? Here in the positive cycle of AC, this capacitor gets fully charged. It gets fully charged, and during the negative cycle of AC, it retains the charge and keeps providing the same voltage as of the positive cycle across RL. So because of this capacitor, when the AC input is negative, still the RL gets positive voltage because of the stored charge in this capacitor. Alright, so this capacitor is connected in parallel, so both the terminals, this and this point, are getting voltages from this capacitor. Now in the negative cycle, so we have this full wave rectifier. So this output, basically this output of a full wave rectifier will be, so since here at this point, when the voltage was dropping, this fall of voltage is retained by this capacitor. So just have a look at the retention of the voltage, and again when the voltage is positive, when the AC is positive, it again retains the positive. Again here we have this constant value of voltage supplied because of the charge retention of this capacitor. So the full wave rectifier, basically when added with the capacitor, acts as a filter, and it filters out the sinusoid curves, positive cycles curves, and gives us the constant value of DC here. So you can see the voltage is very constant, and it is not very like the sine wave which we got as a output waveform in the full wave rectifier.